All right, we are on names and formulas of inorganic compounds, and let's take a look at the warm-up. It says, ions are charged atoms or charged groups of atoms. Ions always associate or bond together in the ratio that results in their charges canceling to form neutral compounds. Complete the table by providing the formulas of the compounds formed by the ions specified. So here you'll see that you have an Na with a +1 charge and a Br with a -1 charge. When you have numbers that are the same in the charges, they just cancel out and you bring them together. The cation would always be listed first and the anion would always be listed second. So when I do the next set, Na+1 and O-2, the 1 and the 2 cross and become subscripts on the other ion. We don't write the number 1 as a subscript. It's a rule. The +1 and the -1 disappear. You can also think of this as if I have an oxygen at the -2 charge, I need to counter that -2 with a +2. So I would need 2 of these sodium ions, which is why you have 2 of them in the formula. Okay. For the next one, Na+1 and OH-1. The +1 and the -1, they just cancel out. They add up to 0, which is how you get your neutral compound, NaOH. For the next set, I've got Na+1 and SO4-2. You want to cross the numbers in the charges to give you Na2SO4. Think of it as if I have a sodium with a +1 charge and a sulfate with a -2 charge, to counter the -2 on the sulfate, I would need 2 of these sodiums at a +1, which is why you see 2 of them in this chemical formula. For sodium and phosphate, Na+1 and PO4-3, you're going to cross the numbers in the charges and you get Na3PO4. Again, if you have a phosphate with a -3 charge on it, you would need 3 of these sodiums at a +1 charge. That's why you have a 3 subscript after the sodium. Okay? Now, moving on, I've got calcium with a +2 charge and bromine with a -1 charge. So you're going to cross the numbers in the charges and you get CaBr2. Again, if I have a +2 charge on the calcium, I would need to counter it with 2 bromines at a -1, which is why you have a subscript 2 on the bromine. For Ca+2 and O-2, the numbers and the charges are the same. They add up to 0 to give me my neutral compound, which is just CaO. For the next one, I've got Ca+2 N-3. The numbers in the charges will cross, giving me Ca3N2. You would logically need 3 of these calciums at a +2 and 2 of these sodiums at a -3 to counter a +6 with a -6 on the calcium and the nitrogen to give you a neutral compound. For the next set, I've got a Ca+2 and an OH-1. There are a couple of ways for me to explain this. If I have a +2 charge on calcium and I have a -1 charge on hydroxide, I would need 2 hydroxides at a -1 to counter this calcium at a +2. So that means when I write the formula, I would have to have 2 hydroxides, which is why you would put the hydroxide in parentheses. You can also think of it as when you're crossing the numbers and the charges, if you're crossing a number down and writing a subscript on a polyatomic ion, which hydroxide is. Polyatomic ions are many atoms together with a charge on them, and anytime you write a subscript on it, you have to put it in parentheses. Okay? For the next set, Ca+2 and SO4-2, well, those counter each other because of the +2 and the -2, so the charges just go away, and we have CaSO4. That's automatically a neutral compound. Here, an Al+3 and a Br-1, we cross the numbers in the charges to give us AlBr3. So if I have a +3 charge on an aluminum, I would need 3 bromines at a -1 to counter it with a -3 to make it a neutral compound, which is why I have a 3 subscript on the bromine. Next, you have an Al plus 3 and an O minus 2. You want to cross the numbers and the charges to give you Al2O3. The next set, you have an Al plus 3 and minus 3. Those charges add up to 0 to give me a neutral compound. So I just get ALN. I just need one of each. For the next one, an Al plus 3 and an SO4 minus 2. Cross the numbers and the charges. You get Al2. You have to put the SO4 in parentheses with a 3 on the outside because you're crossing a number down and writing a subscript on a polyatomic ion. You can also think of it as I need 2 aluminums at a plus 3 to give me a plus 6 overall on the cation aluminum. And then I would need 3 of these sulfates at a negative 2 to give me a negative 6 to counter the plus 6 that I have on the aluminum. That's why you have 2 aluminums in the neutral compound and 3 sulfates in parentheses. The last one, you have Al plus 3, PO4 minus 3. The numbers and the charges just disappear because they create a neutral compound when you add those together. Okay? Now, NH4, I have NH4 with a plus 1 charge, Br with a minus 1 charge. That adds up to 0. I just need one of each in my compound. When I have NH4 plus 1 and N minus 3, when I cross those charges, it tells me I need to have 3 NH4s with 1 nitrogen because that would give me a plus 3 charge on ammonia to counter the negative 3 charge on the nitrogen. So that's why you see 3 NH4s in parentheses in the neutral compound. For the next one, I have an NH4 and an OH with a plus 1 and a minus 1 charge. Those just cancel out because they add up to 0, so I have NH4OH. On the next one, I'm going to have 2 NH4s because I crossed that 2 charge over from sulfate. I would need 2 NH4s because that would give me a plus 2 overall on the cation here. And then I can counter it with a negative 2 on the sulfate to give me a neutral compound. When I break together NH4 and PO4, that's going to give me 3 NH4s with 1 PO4 in the neutral compound. The last row, SN plus 4 and Br minus 1. Cross the numbers and the charges to give you SN Br4. Then SN plus 4 and O minus 2. Here's a little trick. When the numbers and the charges are divisible by the same number, you have to simplify them. So that means this would become a plus 2 and a minus 1 because 2 goes into plus 4 and minus 2. Then you can cross these charges to get SnO2 because you would need 2 oxygens at a negative 1 to counter the plus 2 on the tin. This third one, Sn plus 4 and N minus 3, you need to cross the numbers and the charges to get Sn3 and 4. Then Sn plus 4 with OH minus 1. You're going to need 4 hydroxides at a negative 1 to counter the plus 4 charge on the cation. This last one, you're going to have Sn plus 4 with PO4 minus 3. Cross the numbers and the charges, you'll get 3 SNs and 4 PO4s in parentheses. Now, we're going to be using this concept when we're writing formulas for ionic compounds and acids. So let's start out by talking about binary ionic compounds. Binary ionic compounds are made of 2 things. That's what binary means. It's going to be a metal followed by a non-metal. The metal is your cation. Metals form positive charges. Your nonmetal is your anion. Nonmetals form negative charges. So what you have to do when you write ionic compounds is the metal goes first, the nonmetal goes second, and that is always how you do it for binary ionic compounds because they're made of two elements. They only contain two types of ions, a cation followed by an anion. Now, when we're naming these, you're going to name the metal ion first, followed by the name of the nonmetal ion second, and the ending of the nonmetal is going to change to "ide." Now, technically, a nonmetal ion ends in "ide" for its name, but I'm just pointing that out to you so you're aware. So let's take a look here at what happens when I bring together a sodium ion with a chloride ion. Well, that would give me sodium chloride. That's because a sodium ion is Na+1 and a chloride ion is Cl-1. So I would simply name that sodium chloride, okay? Now, if we take a look at this note here in the paragraph, it says, note that the sign of the ion charge plus or minus is written after the numeral. For example, an aluminum ion is denoted as Al3+ rather than Al+3. Technically, there is no formal rule saying that that's the way we have to do it. I follow the format where you have the charge first, followed by the number after the charge. That's how I do it on Canvas, that's how I do it on paper, that's how I do it everywhere, okay? This is just another format, but I would prefer that you use it where we have the charge followed by the number, especially when you're typing things into Canvas, okay? Okay, let's take a look down here. When we're making ionic compounds by bringing ions together, we're trying to make it so that the charges add up to 0 to give us a neutral compound. So for instance, if I'm bringing together aluminum and sulfide ions, the aluminum ion has a +3 charge, the sulfide ion has a -2 charge. So logically, I would need 2 aluminum ions to give me a +6 and 3 sulfide ions to give me a -6, and those charges would add up to 0 to give me this neutral compound, which is Al2S3, okay? Now, you can either think of it logically as, well, I've got to have so many of each ion to get my neutral compound, or you can look at the numbers in the charges, the +3 and the -2, and the 3 comes down as a subscript on the sulfur, and the 2 comes down and is a subscript on the aluminum, and the plus and the minus just go away, okay? Now, let's take a look at this compound here. We have a Pb+4 and an S-2. So this is technically a lead Roman numeral 4 ion and a sulfide ion. Now, when the numbers in the charges can be simplified, meaning divisible by the same thing, then you need to simplify them. So that means that this would become Pb+2 and this would become S-1, and then you can cross them to give you the PbS2, which is what they have here. This type of simplification happens maybe once on an assignment. It doesn't happen that often. Okay, let's talk about multivalent ions. So a lot of the metals on the periodic table have assigned charges. Those are metals that are in group 1 and 2, and that includes aluminum, zinc, and silver. Technically, it also includes gallium and indium and cadmium in that little triangle off to the right-hand side in the transition metal region that's towards the metalloids. All of the other metals, including the metals that are underneath the stair step on the periodic table, they do not have assigned charges. That's why they don't have shading over them, okay? So multivalent ions are going to be the metals that have more than one form of a stable ion. So these are transition metals in the middle between groups 3 and 12, but it also includes some of the metals that are underneath the stair step on the right-hand side. They're underneath the nonmetals. For example, iron has 2 stable ions. It has Fe+2 and Fe+3. So you would call these the iron Roman numeral 2 ion and the iron Roman numeral 3 ion. Now, when you are typing things like this into Canvas, I have a space after iron before this parenthesis, and then I have a space after this last parenthesis before the word ion. So it's iron space parenthesis, Roman numeral 3, which are capital I's, close the parenthesis, then you have another space, ion. So we use transition metals to indicate the charge on these multivalent ions or transition metals that are capable of having more than one charge, okay? We do not use Roman numerals for aluminum, zinc, silver, gallium, indium, or cadmium, nor do we use Roman numerals for any group 1 metal like lithium, sodium, potassium, rubidium, cesium, francium, nor do we use them for group 2 metals, which are beryllium, magnesium, calcium, strontium, barium, radium. Okay? Okay, now let's take a look at some practice problems on the next page. We're writing the formula for some binary ionic compounds. So you would look at your periodic table. Lithium is Li. It has a +1 charge. Sulfide is sulfur. It has a -2 charge above its group. You can cross the numbers in the charges to give you Li2S. For B, chromium 3 oxide, we have Cr with a +3 charge. This Roman numeral 3 tells you what that charge is on the metal. It will always be positive. And then oxide is oxygen with a -2. You're going to cross the numbers in the charges to give you Cr2O3. If I'm doing C, which is aluminum chloride, aluminum has an assigned charge of +3. Chlorine is -1. Cross the numbers in the charges to give you AlCl3. We do not write the number 1 as a subscript. Lead-2 sulfide. Pb+2, this Roman numeral tells you that you have a +2 charge on the metal. Metals always have positive charges. Sulfur is a -2. When the numbers and the charges are the same, they just cancel out. You get Pbs. For E, tin 2 iodide is Sn+2, I-1. Cross the numbers in the charges to give you SnI2. Remember, we do not write the number 1 as a subscript. Zinc bromide. Zinc has an assigned charge of +2. We're going to cross the numbers in the charges. We get ZnBr2. We do not write the number 1 as a subscript on the zinc. Now, for number 2, we're going to name these binary ionic compounds. Now, when you're naming binary ionic compounds and you have a metal that has an assigned charge, you can just name it. Super straightforward and easy. But if you have a binary ionic compound that contains a transition metal that may have varying charges, which is a multivalent ion, you have to calculate its charge. So I'm going to do A, D, and E first, and then we'll go back and do the rest. Zn is zinc. Has an assigned charge, I can just name it. O is oxygen, I change the ending to "ide", that is oxide. D, Na is sodium. I is iodine, I change the ending to "ide", that's sodium iodide. For E, K is potassium. S is sulfur, I change the ending to "ide," I get sulfide. Now, when I'm doing B, C, and F, anytime you have a transition metal in which you have to figure out the charge on the metal, you calculate the charge on the nonmetal first. I have 4 chlorines at a -1. Overall, I have a -4 on the anion on the right side. I have to counter that with a +4 on the lead. That means that I would have to have a +4 charge on the lead because I only have one of them. So that means this would be called lead, Roman numeral 4, chloride. Change the ending of the nonmetal to "ide." For C, you have 2 chlorines at a -1. That gives you a -2 overall on the anion. If I have 1 copper, the charge on the copper is going to be a +2 because the 1 times +2 would give me a +2 charge on the cation, which will counter the -2 charge on the anion to give me my neutral compound. So this is called copper, Roman numeral 2 for this charge that we just figured out on the copper, and then change the ending of the nonmetal to "ide." For F, I have 1 oxygen, its charge is -2, so that means I have a -2 overall on the anion. I have 1 chromium, which means its charge must be +2. So this would be chromium, Roman numeral 2 for this charge on the chromium, oxide. Okay, let's talk about polyatomic ions. Polyatomic ions are when we have a group of atoms together, they're bonded to each other, and they have a charge. The charge could be positive, it could be negative. A lot of polyatomic ions are oxyanions, which means that they contain oxygen. For instance, nitrite is NO2 -1. Sulfite is SO3 -2. Nitrate is NO3 -1. Sulfate SO4 -2. And when you are looking at polyatomic ions that contain oxygen, they are likely going to be following that 3-4-4-3 trick that I've taught you. And you can use that to determine their formulas and to determine their names. Okay, so for instance, if you're looking at chlorine and you look underneath chlorine at the 3-4-4-3 row, which tells you how many oxygens are in an 8-ending polyatomic ion, you have 3 oxygens in chlorine, which is why chlorate is ClO3 -1. If you subtract 1 oxygen from an 8, you get an ite, which would be ClO2 -1 as an example. If you subtract 1 more oxygen, you're going to get a hypoite, which is how we get hypochlorite, which is ClO -1. Notice we didn't write the number 1 subscript here. If you add an oxygen to the 8s, you're going to get a per8, and that's how we got ClO4 -1. Now, what happens if we have the prefix bi before the name of a polyatomic ion? Well, that means you add a hydrogen to it. For instance, carbonate is CO3 -2. If I have hydrogen carbonate, also known as bicarbonate, those ions have a hydrogen in front of carbonate. So that means they took an H+1, added it to a CO3 -2, and the +1 in the hydrogen ion and the -2 in the carbonate ion get added together. And that gives you HCO3 -1. If I have a hydrogen in front of sulfate, I get hydrogen sulfate, which is also known as bisulfate. So that means the +1 charge on hydrogen is added to the -2 charge on sulfate, which gives me HSO4 -1. Polyatomic ions are going to associate themselves with oppositely charged ions to form ionic compounds. So that means I can combine a nitrate ion with calcium to get calcium nitrate, or a hydroxide ion with calcium to get calcium hydroxide. Okay? Some of the unusual polyatomic ions you're going to find on the bottom left of your periodic table. Those would be things like hydroxide, acetate, chromate, dichromate. They will all be down there if they're not following the 3-4-4-3 trick. This also includes the ammonium ion. Okay, now let's take a look at some practice problems here. Write the formula for the following ionic compounds. Now, these ionic compounds are also going to contain a polyatomic ion. Just so you know, ionic compounds, technically, any compound that contains a metal or the ammonium ion. So ionic compounds will begin with a metal or the ammonium ion. Now, barium sulfate. Barium is Ba with a +2 charge. Sulfate is SO4 with a -2 charge. You use the 3-4-4-3 trick to get that formula. The numbers and the charges are the same, so they cancel. So we get BaSO4. The next one, B, is silver nitrate. Silver has an assigned charge of +1. So this would be Ag +1. Nitrate you can get using the 3-4-4-3 trick. But since there's a circle around nitrogen going over to group 17, what that's telling you is to use that numbering system when oxygen is attached to nitrogen. The numbers and the charges are the same, so they cancel. We get AgNO3. For C, we have mercury 2 bromide. So this would be Hg +2, Br -1. Cross the numbers and the charges to give you HgBr2. D, tin 4 oxalate. So tin is going to be Sn with a +4 charge because that's what the Roman numeral is. And then oxalate is going to be on the bottom left of your periodic table. It is C2O4 -2. And you'll notice the numbers and the charges are divisible by 2. So this would become a -1. This would become a +2. And then you can go ahead and cross those charges to give you Sn parentheses C2O42 because you have to denote how many of those polyatomic ions you have in the compound with parentheses. E, aluminum dichromate. Aluminum is Al +3. Dichromate is on the bottom left of your periodic table. It's Cr2O7. You're going to cross the numbers and the charges to give you Al2. Put the Cr2O7 in parentheses with the 3 on the outside. F, potassium fluoride. It's K +1, F -1. The numbers and the charges cancel. That's how you get Kf. Now, for naming the rest of these ionic compounds, remember, you've got to be aware of which ones contain transition metals that require you to calculate their charge. These are your multivalent ions. I'm going to do the others first. Zn is zinc. When you have parentheses, name what is inside the parentheses. OH is hydroxide. For D, Na is sodium. This probably does not look familiar to you. This is also known as C2H3O2, which is on the bottom left of your periodic table. CH3COO is another way of writing acetate. So this is sodium acetate. For E, this is Mg, magnesium. And then I is iodine. We change the ending to iodide. Now what I'm going to do is I'm going to calculate the charge on the transition metals for the rest of them. But remember, you always have to figure out what the charge is on the nonmetal first. If I have one oxygen at a -2, that means I would have to have a +2 charge on the tin because I only have one of them. So this is tin, Roman numeral 2 for that charge, oxide. When you have a polyatomic ion with parentheses, that number outside, the 2 tells you you have 2 ClOs. The charge on ClO is a -1. So that means I have a -2 overall on the anion. If I only have one copper, its charge would be a +2. So this is copper, Roman numeral 2 because of that charge. And then you name what is inside the parentheses. That is hypochlorite because it's oxygen attached to chlorine. So you would use that 3-4-4-3 trick numbering system. Here on F, you don't have a parenthesis around the Cr2O7, which means you only have one of them because we don't write parentheses on a polyatomic ion if we only have one or we're writing a subscript of 1 on it. If you look at the bottom left of your periodic table, you will notice that you have Cr2O7 there, and you can see it has a -2 charge. If I have one iron, its charge must be +2 to counter that. So this is iron, Roman numeral 2 for that charge that we just figured out. Cr2O7 is dichromate. Okay, now let's talk about binary molecular compounds. Molecular compounds are compounds that are made of nonmetals. When we use Greek prefixes, that is indicating in the name that this is a molecular compound. The Greek prefixes are on your periodic table in the middle towards the bottom in a column. We don't cross charges here. We'll be using these Greek prefixes over here on the left-hand side. 1 is for mono, 2 is for di, 3 is for tri, 4 is for tetra. We go all the way to 10. Mono, you will use this with 1 oxygen. And for instance, if I have CO2, carbon and oxygen are nonmetals. They're on the right side of the periodic table. So when I name it, I have 1 carbon, so I just call it carbon, no prefix. And then I have 2 oxygens, so I would put di in front of oxygen's name, and I would end the second nonmetal in "ide." For instance, here, xenon tetrafluoride, I have 1 xenon, which is Xe. I have 4 fluorides because of the tetra, so I put a 4 on the fluorine. That gives me XeF4. There's no crossing of charges, and I'm only using mono if I have 1 oxygen. Here for P4S10, this is tetraphosphorus decasulfide. Tetraphosphorus is one word, decasulfide is another word. Let's take a look here at these practice problems. So we're writing the formula for the following molecular compounds. Nitrogen monoxide, that would be NO. Nitrogen dioxide, NO2. Dinitrogen tetroxide, N2O4. Do not simplify subscripts in molecular compounds because that would give you something totally different. N2O4 simplified is NO2. That's nitrogen dioxide in B. D, dinitrogen trioxide, N2O3. Number 2, name the following molecular compounds. PCl5. This is phosphorus, pentachloride. B, SO2, sulfur dioxide. C, carbon monoxide. I use the prefix mono because I had 1 oxygen. D, diphosphorus pentaoxide. Now, let me point out a couple of things here. You'll notice "ide" is only on the ending of the second nonmetal. And be careful when you're naming pentoxide. Get rid of the A. This should just be pentoxide. Okay, so just be careful there. Okay, let's talk about hydrates. Hydrates are salts that have water attached. And they will have water attached. You'll see a little tiny multiplication symbol after the ionic compound with however many waters are attached to it. Anhydrous would be a salt without water attached. Some anhydrous salts are hygroscopic, which means they absorb water from the air and they form hydrates. We often use hygroscopic salts to keep the air dry in containers. They're known as desiccants. And you'll see pouches with silicate salts in like shoe boxes or guitar boxes to absorb the water in the air to keep the air dry. A lot of labs have special airtight glass containers to store these hygroscopic salts. And let me show you on the next page what this looks like. So here you will see I have water attached to an ionic compound. There's a little tiny circle multiplication symbol here. So this is actually called copper 2 sulfate heptahydrate. So the Greek prefix is indicating how many waters are attached. If we're looking at practice problems down here, problem number 1 says, write the formula of each of the following hydrates. So barium chloride dihydrate would be Ba plus 2 for barium, Cl minus 1 for chloride. Cross the numbers in the charges to give you BaCl2. And since there are 2 waters attached, you would put a little multiplication symbol with 2H2O. Sodium carbonate, monohydrate. Sodium is plus 1. Carbonate is CO3 minus 2. Cross the numbers in the charges to give you Na2CO3. And monohydrate means you have 1 water attached. Iron 3 nitrate nonohydrate. So this would be Fe plus 3, NO3 minus 1. Cross the numbers in the charges. Put the NO3 in parentheses with the 3 outside, and then you'll have 9 waters attached. For part D, barium hydroxide, this is Ba plus 2, OH minus 1. Cross the numbers in the charges. You'll have parentheses around the OH, and you have 8 waters attached. Now, if we're naming these hydrates, for number 2, you have to calculate the charge on cobalt and iron, so I'm going to come back and do those. C would simply be sodium. Cr2O7 is on the bottom left of your periodic table. It's dichromate. And then you have 2 waters attached, so this would be dihydrate. The dihydrate is one word. D, this is magnesium sulfate. And then since you have 7 waters attached, this would be heptahydrate. Then up here, I've got a -1 charge on the chlorine with 2 of them, so that means my charge on cobalt is a 2. So this is cobalt, Roman numeral 2, chloride. And since I have 6 waters attached, this would be hexahydrate. I have a -1 charge on the chlorine, so that means my charge on iron is a 3. This is iron, Roman numeral 3, chloride, tetrahydrate. Let's talk about acids. Acids acids are going to have they're going to begin with a hydrogen. They're going to have one or more hydrogen ions bonded to an anion. They're going to be dissolved in water. They're a special type of molecular compound that can be induced to form ions in water. And the names of ions of acids are based on the name of the anion formed. If the anion, let me move this over. If the anion doesn't contain oxygen, the prefix hydro precedes the name of the anion, and ic replaces the ide in the anion's name. For instance, HF does not contain oxygen. So we begin it with hydro, change the ending on fluorine to ic, it becomes hydrofluoric acid. HCl is the same way. It does not contain oxygen. It begins with hydro, change the ending on the nonmetal to ic, becomes hydrochloric acid. Same thing for hydrogen cyanide. So this would be hydrocyanic acid, etc. Now, there are some exceptions. For instance, when you have sulfur with hydrogen for H2S, no oxygen there. This is hydro. You might think that this is sulfuric acid, but it's really hydrosulfuric acid. It sounds better than hydrosulfic acid, so that's why we use it. Now, if your anion contains oxygen, ic replaces 8 in the anion's name. If you have an OUS and an ite, if you end in ite, replace it with OUS. So for instance, H2SO4. SO4 is sulfate. Change the H to ic, you get sulfuric acid. H2SO3. SO3 is sulfite. Change the ite to OUS, and you get sulfurous acid. Okay? Let's take a look at some formulas down here. Something to mention. Technically, binary acids, which don't contain oxygen, okay? They require a state of matter or an AQ after the formula, whereas oxy acids, which are also known as ternary acids, do not. So when I'm writing the formula for hydrofluoric acid, I know it doesn't contain oxygen because it begins with hydro. I partner it with fluorine. The numbers in the charges cancel. I get HF. Technically, you have to have the AQ after the formula. For hypochlorous acid, if it ends in OUS, that means I started with hypochlorite. And if it's an acid, it begins with hydrogen. The formula for the hypochlorite ion is ClO -1. The numbers in the charges cancel, and you'll get HClO. You don't have to include the AQ after the formula for acids containing oxygen. It is already implied that it is dissolved in water. The reason you have to do it for these acids that don't contain oxygen or binary acids is because without the AQ, that's technically hydrogen fluoride. But with the AQ, it's hydrofluoric acid because it's dissolved in water. If you put the AQ on an acid containing oxygen, it's fine. It's just not required. Phosphoric acid, if it ends in ic, that means you started with phosphate. So acids begin with hydrogen. The phosphate ion is PO4 -3. Cross the charges, you get H3PO4. Hydrosulfuric acid. The hydro is telling me that there is no oxygen. Sulfur is S negative 2. Cross the numbers in the charges, you get H2S, and that has to be dissolved in water because it doesn't contain oxygen. It's a binary acid, so include the AQ. Now, if I'm naming this acid, remember we saw this formula before. It's the acetate formula, written a different way. So if I have acetate, when it ends in ate, you change the ending to ic, and you write acid after it. So this is acetic acid, and you do this with acids containing oxygen. Here, H2SO3. SO3 is sulfite. When it ends in ite, it changes to OUS, and then you write acid after it. So this is sulfurous acid. Sulfurous sounds better than sulfus. That's why we do it. C. CO3 is carbonate. When it ends in ate, it becomes ic, and you write acid after it. So this is carbonic acid. D, HI. Technically, there should be a little AQ after this. This does not contain oxygen, so we put hydro in front. Change the ending of this nonmetal to ic, so it's hydroiodic acid.